Okay, so yesterday we started talking about this idea of counting things by weighing things. And uh, we said that atoms were so minuscule in size that we had to use something called atomic mass units, or AMUs. AMUs. Now, atomic mass units, they're just another invented mass unit that enables us to talk about very tiny things. And I mentioned that that number on the periodic table underneath the element represents the number of atomic mass units for, say, for one atom of those things. In copper, for example, 63.546. But I also said that there were these things called isotopes, and not every copper atom has the same number of isotopes. So I want to show you uh, uh, how we get those numbers, because we have to learn something called a weighted average. But before I do that, I just want to tell you, I want to ask you, um, I know that there are 6.022 times 10 to the 23rd AMUs is equal to 1 gram. So before we get into this, I want you to tell me how many grams there are in an AMU. I'm going to pause, see if you do it. So we can see approximately that the one atomic mass unit, 1 AMU, is approximately 1.7 times 10 to the negative 24 grams, 1.66 times 10 to the negative 24 grams. So you can see that's such a small number. It's got, bunches of zeros until you get to the first non-zero digit. So we're going to use this later on to equate AMUs to moles and grams, but that'll come in a little bit. But first of all, let's see what that weighted average is all about. And I had to look, these are hard to make up off the top of your head because you need the exact percentages. So let's take a look at copper since I mentioned copper. I said copper had this hypothetical copper atom. It's going to have an atomic mass of 63.546. Okay. Now, let's see how that number comes about. Because you think if we just have, one type of copper ion or copper atom, it should just be the number of protons, plus the number of neutrons. So I have the percentages. Now these are the two ions, two isotopes. I'm sorry, two isotopes of copper. I have copper, and it's copper 63. And don't forget what that number represents. Copper has 29 protons, and that 63 is the sum of the neutrons and protons. And we are told that 69.09% of all copper atoms are this 63 atomic mass units. So, and we're told that, did I get that right? Yeah, and we are told that 30.91% of all copper atoms are called copper 65 atoms. So what we would do, if we want to go ahead and get the weighted average of these two, what we would say is 0.6909, change your percentage to a decimal, times 63 AMUs, plus 0.3091, that's changing the percentage to decimal, times 65, because that's the mass number there, AMUs. And let's figure out what that equals. So let's get our calculators out and see if we can get that number. point, let's clear that, 0.6909 times 63 plus 0.3091 times 65. And when you go ahead and do this, you end up with 63.6 atomic mass units. And you look at the periodic table and you say, yeah, I get 63.546. Well, that's because this has a mass slightly different than 63. This has a mass slightly different than 65. But I'm using this as an illustration to show you that we do a weighted average and we get that number that's very close to the periodic table. If we knew the exact atomic mass units of that isotope and that isotope, then this would come out closer to 63.55. Okay. So anytime you see a problem and you want to calculate that average atomic mass, you have to know the percent abundance of each of these isotopes. Let me see if I can pull one from the back of the book, and you can take a look at it. Okay. And there's a good one. And put it on the board. I'm going to pause this. And, okay, as I just said, we're looking at 3 isotopes of magnesium. Magnesium 24, 25, and 26. These are the actual masses and atomic mass units of each of the isotopes. Put a 0 here, I guess, for significant figure purposes. And these are the relative abundances percentage-wise. So I'd like you to take a few minutes now and see if you can figure out, can I come up with that number on the periodic table of approximately 24.305 atomic mass units? Be right back. Okay, the question was, in order to do this, are we supposed to use the percent abundance or the mass? Well, we have to use both. Okay, think of it this way. Let's say, for example, you're taking a class and you know that your homework counts for 10% of your grade. And you know that your exams count for 50% of your grade. Your labs count for 30% of your grade. How far am I now? 30 plus 50 is 80 plus 10 is 90. And your lab counts for 10% of your grade. If you were to figure that out, you would take your score from your exams, multiply that by the percentage plus the decimal version of the percentage. Your scores for your homework, multiply that by the decimal version of the percentage, et cetera, and then add them all up. Let's call it a weighted average. It's not like a straight average where we just say I'm gonna add these 3 up and divide by 3. Because they occur in different amounts. Like most of this magnesium is right around 23.9. Okay, so, and if I look at magnesium, it says 24.3. There's not a lot that's higher than that. So let me show you how to do this. And then we can go and... Why do I always lose my pens? Okay, so now watch. This is going to give our mass and atomic mass units. But remember, what we have to do is we have to say percentage to decimal. 0.7899 times 23.980 AMU plus, we've got 0.1000 times 24.985 AMU, okay, atomic mass units. We have to have the unit on there, plus 0.1101 times 25.983 AMU, okay?
So you're basically doing that and multiplying it by that.
That's all you're doing, Anna. You are changing that to a decimal, multiplying it by that. That's this isotope's contribution to the average. Same thing here. Same thing here. And let's see. Let's do this and see what you come up with. Okay, so I ran through the calculations, and I come up with the weighted average for the atomic mass as being 24.301 AMU. So let's look at the periodic table, 24.305. Okay, so we're very, very close. I don't know how accurate these numbers are. I'm sure they're very accurate, but there's just a very tiny discrepancy. But you can see though how we get this number. I hope. So I would be prepared to practice a couple of those, and I could certainly assign a couple of those to you for homework. Okay, so that's a fun exercise. We learn where that number comes from because of the different isotopes. But how does it help us? How does it help us in doing chemistry? Well, this is nice to know. It's nice to know where that number comes from. But we have that relationship between atomic mass units and grams. So we can figure out the number of grams in one atom of each of these. And then what we can do is if we multiply by Avogadro's number, we're going to figure out how many grams per mole. If you remember from yesterday, Avogadro's number, and this is definitely one you should get tattooed on your arm, right here. You can wear your hoodie and campaign and have all the tattoos of equations on your arm, and like that guy running for Senate. Tattoos of all the equations of chemistry. So, how does this help us? Well, the number of AMUs, right, is also equal to the number of grams in a mole. And what was that number? What was that number that was so important to us? We learned yesterday, we saw in the last 5 minutes in the video. Remember the guy with the weird eyes? Had those like Avogadro eyes? Oh, I said his name. Avogadro. He was a weird looking dude. He had like that big nose and like that hair. Dr. Doofenshmirtz. That kind of looks like Avogadro, actually. Exactly looks like he was a creep. Scientists, I'll tell you, scientists in general, and we'll look at scientists because they're creepy. They're either physically unattractive or socially awkward or both. Okay? I fall into the both category. So anyway, his number was 6.022 times 10 to the 23rd things in a mole. And the mole, by the way, is abbreviated MOL, saves us a lot of ink. So if we were able to do the math and say, I'm going to convert from atomic mass units to moles, you would find out that that's the same number of grams in a mole of something as it is atomic mass units in an atom of something. So let me show you some examples. Let me erase Avogadro. Poor guy. Wait till I show you pictures of Niels Bohr. He was a real winner. Lavoisier and all the rest of them. Let's take a look at something like copper. If you see that 63.546, that means two things. That means how many atomic mass units are there in one atom. Of course, that's kind of a weird thought since we don't know which isotope we're looking at. But it also means that's how many grams there are in a mole of this stuff. So if I want 1 mole of copper, I have to go to the balance and I have to mass out 63.546 grams of copper. So the cool thing about this is 63.546 grams of copper contains 6.022 times 10 to the 23rd atoms of copper. So we can count by, I'm going to say weighing, but we know we're getting the mass. Sometimes I get sloppy. So we go and weigh out 63.546 grams, and we have, that is 1 mole. So it's also equal to 1 mole. Now, big deal. So you know how many grams there are in 1 mole. What happens, though, let's say if I've got a chemical compound like H2O, dihydrogen monoxide, as we like to call it, water. I say to you, all right, I want 1 mole of water. How many grams do I have to mass out? Simple. You just add, you go to the periodic table and say, well, I've got two hydrogens, each at 1.01 grams per mole. And I have to add to that my one oxygen. I've got one oxygen, and it's 15.999. We usually just call it 16.00 grams per mole. Okay, so you add those two up, and you get 18.02 grams per mole for water. Just add them up. There's nothing to it. You can calculate how many grams in 1 mole of any chemical compound. We've been spending a week naming chemical compounds. So we can go ahead and look at some, and you can tell me how many grams per mole. Let me put a couple on the board for you to try. And by the way, that has a certain name. If I say water is 18.02 grams per mole, that is called the molar mass. Molar mass. Sometimes, now I'm going to give you three words that mean the same thing, depending upon who's teaching you chemistry or what book you're reading. Sometimes it's called the molecular weight. That's kind of an old, outdated term. We don't use that too often. Sometimes we call it the formula weight. Okay. These are three names that mean the same thing. How many grams in a mole of a chemical compound? And we could have something called the atomic mass. The atomic mass is just the number of grams in a mole of a certain atom, like magnesium is 24.3 grams. So let's try a couple of chemical compounds. Right, let's say I've got, first of all, this is going to be a good question because I'm going to write a chemical formula down. I want you to write the name of that formula and calculate the molecular mass or the molecular weight, the formula weight of this compound. Cu in September, CuSO4. Give me the molar mass of copper sulfate.